Assalamu alaikum. My name is Muhammad Shoaib. In this lecture, I am going to discuss regioselectivity with respect to the disconnection approach. The background knowledge of conjugate addition and alkylation of enolates is necessary for this lecture. Chemoselectivity is that how to react one functional group rather than another, and regioselectivity is how to react one specific part of a single functional group and not the other. Here, the anions of phenols are alkylated at oxygen to give ether, while enolate anions are alkylated at carbon to give a new carbon-carbon bond. In both of these cases, the products are certain. But there are some cases where we may want different results. For example, alkylation of 2-butanone, as given here, may give 3-pentanone. Here is 3-pentanone or 3-methyl-2-butanone depending upon the reactants used. Similarly, nucleophiles are either added directly to the carbonyl or in conjugate fashion to the enone. Here is a direct addition of nucleophile to the carbonyl group, and here it is a conjugate addition of nucleophile. Now let's see the regioselective alkylation of ketones. Here is the analysis of 3-benzyl-2-hexanone. First benzyl is removed, as shown here, and activated group, that is ester COOET, is added, which will promote alkylation both times. In synthesis, the ester is first alkylated by using propyl bromide, and sodium methoxide will remove the proton present at alpha position of both the ester and the keto group, and the propyl is attached at this carbon. And the next, sodium methoxide will remove a proton from that carbon, and the benzyl is attached here. In the last step, ester is hydrolyzed and decarboxylated. Next is the regioselectivity of enolate. Acetone is alkylated on one side by using propyl bromide. It is then again treated with LDA, which is a hindered base, and will form enolate on a less hindered side. That's why benzyl will be added on the other side. As shown here, first propyl is added on one side and then the benzyl will be added on other side. In the second example, 2-hexanone is benzylated. It is 2-hexanone. LDA, it is a strong and hindered base. It will remove a proton from less hindered side and benzyl will be attached on this carbon. It looks a clean reaction, but there are two types of product. One is major product, which is 87%, and other is the minor product, which is 13%. Remember that more substituted alkene is more stable. Therefore, the chances of more substituted enolates are not necessarily overruled. Even the base is very hindered. In 2-methyl-cyclohexanone, LDA will attack less hindered side and will be benzylated via less substituted lithium enolate. Next, we see the analysis of 2-methyl-1-phenylhexane 3-one. It is possible from 1,3-dicarbonyl compounds, disconnecting acer derivatives which could be prepared by malonate. Synthesis involves first methylation at activated carbon and then the benzylation at the same carbon The ester group is hydrolyzed and converted into acid. One acid group is decarboxylated and another is converted into acid chloride. By using di-N-propyl cadmium, target molecule is obtained. Next is regioselectivity in nucleophilic addition to enones. Enones can undergo two types of nucleophilic addition, that is, direct addition to carbonyl called as 1,2 addition or conjugate addition on carbon-carbon double bond which is called as 1,4 or Michael addition. The general principles of regioselectivity are that conjugate addition is thermodynamically favored and takes place by less basic nucleophile as the weak carbon-carbon double bond is lost, but the strong carbon double bond oxygen is retained. While the direct addition is kinetically favored and is easily reversed when the nucleophile is more stable, and in competing reaction, in case of more stable nucleophile, 1,4 addition predominates. Here, the reactivity of reagent, or we can say it, to some extent it is a steric factor. More electrophile alpha-beta unsaturated carbonyl compounds such as aldehyde and esters tend to do direct addition. As Grignard reagent is added to the carbonyl group in cyclopentene carbaldehyde, but it may add in conjugate fashion to alpha-beta unsaturated esters if the ester group is large, such as candibutyl as shown in the second example. Addition product also depends upon the type of nucleophile. Softer, less basic nucleophiles are good at conjugate addition, while the hydride and alkoxide are better at direct addition. That's why aldehyde and ketones and esters are reduced by hydrides, while catalytic hydrogenation reduces only carbon-carbon double bond, as there is no ionic reaction. Another example is the preparation of unsaturated alcohol. Reduction of di in ester with lithium aluminium hydride give the target molecule. The very basic and aggressive nucleophile organolithium tends to do direct addition to alpha-beta unsaturated carbonyl compounds. The less basic Grignard reagent may add in either sense. If the given enone reacts with Grignard reagents in the presence of cuprous iodide, the conjugate addition product is obtained, and with lithium organocuprate, enolate is formed by the product is same as the Grignard reagent. Here is a stereochemistry. Addition of cuprate to a cyclic enone followed by the reaction with an electrophile give anti-stereochemistry. But when the one side is already in place, addition of diallyl copper lithium followed by the protonation give the syn compound as shown in the second example. When the thermodynamic control is dominated, the cis ring junction is preferred, as between the flat 5-membered and 6-membered rings. The molecule prefers a folded conformation. Below is given that the stereochemistry may be created during the additional steps, as the addition of substituted cyclohexanone in both examples, when reacted to cuprates, give anti-conformation, almost in 100%. The addition of cyclohexanone to lithium di and propynyl cuprate, the stereochemistry of alkene double bond is retained. It is the same as in propynyl bromide and the product. And that's all about regioselectivity.